Mars appears to us now as a world of rust-colored dust and ancient stone. From orbit, its surface stretches out in shades of orange and brown, punctuated by darker volcanic plains and brighter polar regions that gleam with frost. The planet measures about 6,792 kilometers in diameter, roughly half the size of Earth, and it orbits the Sun at an average distance of 228 million kilometers. This distance places it firmly in what scientists call the habitable zone, where conditions could theoretically support liquid water on a planetary surface. Yet when we examine Mars today, we find a world where water cannot freely flow. The atmospheric pressure at the Martian surface averages around 600 pascals, less than 1% of the pressure at Earth's sea level. This thin envelope of air, composed of 95% carbon dioxide with traces of nitrogen and argon, creates conditions where liquid water is fundamentally unstable. When ice warms on the Martian surface, it typically sublimates directly into vapor rather than melting into liquid. When any liquid does momentarily form, it quickly boils away into the dry atmosphere or freezes solid in the cold. Surface temperatures on Mars vary dramatically with location and season. At the equator during summer afternoons, the ground can warm to about 20 degrees Celsius, pleasant by Earth standards. But this warmth is fleeting and localized. As the sun sets, temperatures plummet to minus 73 degrees Celsius or colder. At the winter poles, thermometers record temperatures as low as minus 153 degrees Celsius, cold enough to freeze carbon dioxide from the atmosphere into dry ice. This is the Mars we observe today, a frozen desert where water exists primarily as ice locked in polar caps and buried beneath the surface. The atmosphere carries only trace amounts of water vapor, far less than 1% of typical levels on Earth. When the Curiosity rover measures humidity at Gale Crater, it records values that hover near zero during the day, rising above 60% only during the coldest hours before dawn when the air is too frigid to hold moisture. But Mars was not always this way. The story written in its rocks and valleys tells of a dramatically different past, one where water moved freely across the surface, carving channels and filling basins, potentially creating environments where life might have emerged. Understanding where that water came from, where it went, and where it exists today forms one of the central questions in planetary science. The evidence for ancient water appears everywhere we look on Mars. Spacecraft in orbit have photographed networks of valleys that branch like river systems, their tributaries joining together in patterns that closely resemble drainage basins on Earth. Rovers on the surface have analyzed rocks that formed in standing water, mudstones that preserve ripples from ancient lake beds. Radar instruments have detected vast quantities of ice buried just below the dusty surface at middle and high latitudes. NASA's strategy for Mars exploration has followed a simple principle: follow the water. This approach recognizes that water is essential for life as we know it, serving as a solvent for biochemistry and a medium where organic molecules can interact. By mapping where water exists on Mars today and where it flowed in the past, scientists hope to identify locations where life might have taken hold billions of years ago, or where it might persist today in protected niches beneath the surface. The search for Martian water has produced discoveries that continue to reshape our understanding of the red planet. Recent findings have revealed that Mars holds far more water than previously suspected, with some estimates suggesting enough frozen water beneath the surface to fill an ocean. Other investigations have shown that small amounts of liquid brine might form temporarily on present-day Mars under specific conditions involving hygroscopic salts. The story of water on Mars turns out to be far more complex and fascinating than early astronomers imagined when they first telescopically observed the planet's polar ice caps in the 17th century. This exploration of Martian hydrology will proceed gently through the many forms water takes on Mars. We'll examine the ice caps that grow and shrink with the seasons, explore the subsurface reservoirs that hold ancient water in frozen form, consider the evidence for primordial oceans that may have covered a third of the planet's surface, trace the dried riverbeds that once carried flowing water, analyze the thin moisture in the atmosphere, decode the chemical signatures that tell us how much water Mars has lost to space, investigate the salts that might enable liquid brines to form today, visit the ancient lake that once filled Gale Crater, examine the water locked in, minerals and rocks, and survey the ongoing search for accessible water resources. The journey ahead will unfold at a measured pace, allowing each detail to settle naturally into understanding. There is no need to rush through these facts about Martian water. The planet has been revealing its secrets gradually over decades of patient observation, and we can explore them with the same unhurried curiosity that drives scientific investigation. As we move through this material, the picture of Mars as a world shaped by water will emerge piece by piece, fact by fact, building toward a comprehensive view of how water has defined the red planet's past and present. At the north and south poles of Mars lie the most obvious reservoirs of water on the planet, the polar ice caps. These gleaming white deposits, visible through even modest telescopes from Earth, have captured human attention for centuries. Giovanni Cassini created some of the first detailed sketches of Mars in 1666, and those early drawings already depicted bright markings at the planet's poles. As telescopes improved over the following centuries, astronomers watched these polar caps grow and shrink with the Martian seasons, leading to speculation about their composition and what they might reveal about conditions on Mars. The northern polar cap, called Planum Boreum, forms a roughly circular dome centered on the Martian North Pole. During northern summer, this permanent cap measures about 1,000 kilometers in diameter. The ice sits at relatively low elevation, with its base at about 5,000 meters below the planetary mean radius and its top reaching about 2,000 meters below this reference level. Despite being in a depression compared to much of Mars, the ice cap rises as a prominent feature when viewed from the northern plains that surround it. The southern polar cap, Planum Austral, differs in several respects from its northern counterpart. It sits at much higher elevation, with its base around 1,000 meters above the mean planetary radius and peaks reaching 3,500 meters above this reference. The southern cap is somewhat smaller than the northern one, though still vast by any terrestrial standard. Both caps consist primarily of water ice, though their seasonal behavior and exact composition reveal important differences. Each polar cap actually comprises multiple distinct layers. At the foundation lies what scientists call the basal unit, ancient deposits of sand and dust cemented together with water ice. These formations may be over 1 billion years old and likely formed under different climate conditions than those that exist on Mars today. The basal unit of the northern cap can be nearly 1,000 meters thick near the center, though much of it remains hidden beneath younger deposits above it. We know about these ancient foundations primarily from exposures visible in the walls of canyons that cut into the polar caps, particularly Chasma Boreal, a massive canyon that slices into Planum Boreum for 570 kilometers. Above the basal unit lie the polar layered deposits, which make up the bulk of each ice cap. These deposits consist of alternating layers of relatively pure water ice and dustier ice, stacked one upon another in formations that can reach 2,000 meters thick in the north. The individual layers vary in thickness from decimeters to several meters, and their alternating composition creates visible banding in high-resolution images. Scientists believe these layers record climate variations driven by changes in Mars's orbital parameters over millions of years. Mars's axial tilt, or obliquity, changes far more than Earth's over long timescales. Currently tilted at about 25 degrees to its orbital plane, similar to Earth's tilt, Mars's obliquity can vary between about 15 and 35 degrees over cycles lasting about 120,000 years. These variations affect how much sunlight reaches different latitudes, influencing where ice accumulates and where it sublimates away. The polar layered deposits preserve this history in their stratigraphy, though decoding exactly which layers correspond to which climate cycles remains challenging. Radar instruments orbiting Mars have probed through the ice to measure its total thickness. The Marcis radar on Mars Express and the SHARAD instrument on Mars Reconnaissance Orbiter bounce radio waves off the ice and detect echoes from layers within it and from the rock beneath. These measurements reveal that both polar ice caps are up to 3.5 kilometers thick in places. The northern cap contains about 1,600,000 cubic kilometers of water ice, which if melted would cover the entire planet in a layer about 11 meters deep. The southern cap holds a comparable volume. The composition of the permanent polar caps was debated for decades. Early observations suggested they might be primarily frozen carbon dioxide or dry ice, since Mars's atmosphere is mostly carbon dioxide and the polar regions get cold enough for it to freeze. However, improved measurements from orbiting spacecraft in the early 21st century established that both permanent caps are composed predominantly of water ice with only a relatively thin coating of seasonal carbon dioxide ice. The seasonal changes in the polar regions are dramatic. As autumn transitions to winter at each pole, carbon dioxide begins freezing directly from the atmosphere onto the surface. This seasonal frost accumulates as a layer roughly 1 meter thick at the North Pole, but as much as 8 meters thick at the South Pole during southern winter. The difference stems from Mars' elliptical orbit. The planet reaches its farthest point from the Sun during southern winter, making southern winters both longer and colder than northern winters. During the long polar night, which lasts about 6 months in Earth time at each pole, temperatures drop below -120 degrees Celsius. At these extreme temperatures, roughly 25 to 30% of the planet's entire atmosphere condenses as frost onto whichever pole is experiencing winter. This represents an enormous seasonal transfer of atmospheric mass. Pressure sensors on Mars landers have directly measured the atmosphere thinning during winter as carbon dioxide freezes out, then thickening again in spring, as the dry ice sublimates back into gas. The spring sublimation of seasonal dry ice creates some of Mars' most dynamic surface features. As sunlight returns to the poles, it penetrates the translucent dry ice and warms the darker ground beneath. Carbon dioxide gas builds up under the ice cap, and when pressure becomes sufficient, the gas explosively ruptures through the overlying ice in geyser-like eruptions. These jets of gas entrain dark sand and dust, which falls back to the surface in fan-shaped patterns. The entire process happens rapidly by geological standards, with new patterns appearing over the course of days or weeks. Beneath and around the permanent ice caps, vast deposits of windblown sand form dune fields. The northern polar region includes Olympia Undae, an extensive sand sea that encircles Planemborium. These dunes, composed of dark basaltic sand eroded from the basal unit and blown by fierce polar winds, create striking visual contrast with the bright ice. Some of these dunes show evidence of current movement, with avalanche faces and ripple patterns that change position between successive imaging sessions. The canyons that spiral through the polar ice caps reveal their internal structure in dramatic fashion. The largest, Chasma Boreal, cuts through the northern ice cap like a knife slice through a layered cake, exposing hundreds of individual ice and dust layers in its walls. Scientists have proposed two main hypotheses for how these canyons formed. One suggests that solar heating causes ice at the cap's edges to sublimate, with the sublimation front spiraling inward as wind patterns preferentially remove ice from certain orientations. The other proposes that strong katabatic winds, generated as cold, dense air flows downslope from the ice cap's high center, carved the canyons through mechanical erosion and enhanced sublimation. Water from the polar caps doesn't stay permanently locked in place. A global water cycle operates on Mars, though it functions quite differently from Earth's water cycle. During northern summer, water ice at the edge of the North Polar Cap sublimates into the atmosphere. This water vapor is transported through atmospheric circulation to other parts of the planet, where some deposits as frost at high latitudes in the southern hemisphere. The process reverses half a Martian year later during southern summer. This cycle means that water molecules that are frozen at the North Pole today might travel to the South Pole in a few years, then return north in a few more years. The stability of the polar ice caps over geological time depends on Mars's current orbital and axial configuration. At the planet's present obliquity and eccentricity, the poles act as cold traps where water ice can persist indefinitely, protected from the sun's warming effect by the thin atmosphere and low temperatures. However, when Mars's tilt increases significantly during its long-term orbital cycles, the poles receive more direct sunlight and ice can sublimate more readily. Climate models suggest that during high obliquity periods, water ice from the polar caps redistributes to lower latitudes, forming glaciers at mid-latitudes instead. Evidence for this redistribution appears in glacial deposits found far from the poles. Radar imaging has revealed formations at middle latitudes that look remarkably like glaciers, with layered internal structure consistent with ice flow. Many of these features are currently covered by a protective layer of dust and rock which insulates the ice beneath from sublimation. These deposits may represent water that migrated from the poles during past climate shifts and remains preserved beneath its dusty coating. The total amount of water locked in Mars's polar ice caps is substantial from a planetary perspective, though modest compared to Earth's ice sheets. The combined volume of both Martian polar caps is roughly comparable to the volume of Earth's Greenland ice sheet, which contains about 2,900,000 cubic kilometers of ice. This means Mars holds enough polar ice to cover its entire surface in a layer about 20 meters deep if melted, though of course the low pressure and temperature would prevent liquid water from pooling in such a scenario. The polar regions of Mars hold particular interest for future human exploration. Water ice concentrated at the poles represents an accessible resource that could be melted, purified and used for drinking water, oxygen production, and hydrogen fuel generation. However, the harsh polar climate poses significant challenges. Winters bring months of continuous darkness and temperatures that would freeze most equipment. Summers offer sunlight but still include regular dust storms and wind speeds that can exceed 400 kilometers per hour as they race downslope from the high ice caps. The detailed structure visible in high-resolution images of the polar layered deposits continues to puzzle scientists. Individual layers show complex patterns where they thin, thicken, and pinch out. Some layers appear wavy, others rough, and still others smooth. Scientists studying these features try to understand how ice flows under Martian gravity, how dust gets incorporated into the ice, and what causes some layers to be dustier than others. The answers to these questions will help reconstruct Mars's climate history over the past several million years. The residual ice caps, which are the parts that survive each summer, maintain relatively stable boundaries from year to year at present. The north residual cap has a characteristic spiral pattern visible in images, with troughs spiraling outward from the pole. This shape may result from the interaction between sublimation processes and the planet's rotation, though the exact mechanism remains debated. The south residual cap lacks the north's prominent spiral structure, but displays its own complex surface patterns, including areas pitted like Swiss cheese where sublimation has carved irregular depressions. Beyond the obvious ice caps at the poles, Mars hides vast quantities of frozen water beneath its dusty surface. This subsurface ice exists in multiple forms at various depths, from shallow frost layers just centimeters below the surface to massive deposits buried under meters of rock and soil, to ancient water potentially trapped kilometers deep in the planet's crust. Understanding the distribution and accessibility of this hidden ice is crucial for piecing together Mars's water budget and planning future exploration. The discovery of abundant subsurface ice at mid-latitudes represents one of the major revelations of Mars exploration over the past 2 decades. The Mars Odyssey orbiter, which arrived at Mars in 2001, carried a gamma-ray spectrometer designed to detect chemical elements in the Martian surface. This instrument works by measuring gamma rays and neutrons emitted when cosmic rays strike the surface and interact with atomic nuclei. Hydrogen absorbs neutrons particularly effectively, so regions with high hydrogen content show a distinct depletion in the neutron signal detected by the spacecraft. Starting in 2002, the Mars Odyssey team began reporting enormous regions with high hydrogen content concentrated in broad bands around both poles. The hydrogen signature indicated the presence of water ice or hydrated minerals, and the simplicity of the pattern suggested ice rather than scattered hydrated rocks. These ice-rich zones extend from the poles down to about 50 degrees latitude in the south and 60 degrees latitude in the north, encompassing millions of square kilometers of the Martian surface. The gamma-ray spectrometer measured hydrogen in the upper meter of soil, revealing that in the most ice-rich regions, the ground contains more than 50% water ice by volume. This ice isn't scattered as small crystals mixed through the soil. Rather, it appears to exist as relatively pure ice beneath a drier surface layer. In many locations, drilling through 30 to 60 centimeters of dry regolith would reach essentially pure ice, what scientists describe as more accurately characterized as dirty ice rather than ice-bearing dirt. Direct confirmation of this buried ice came from an unexpected source. In 2008, the Phoenix Mars lander set down at 68 degrees north, latitude well within the predicted ice-rich zone. The lander's robotic arm dug shallow trenches to examine soil properties. When the scoop excavated one trench, it exposed bright white material in the trench walls. Mission scientists initially suspected this might be salt deposits, but over the following days, something remarkable happened. The bright material disappeared. Time-lapse images showed chunks of bright material in the trench walls gradually shrinking and vanishing completely over the course of 4 Martian days. The disappearance could only mean one thing: the bright material was water ice, and it was sublimating directly from solid to vapor in the Martian environment. The local temperature of around -30 degrees Celsius and the very low humidity provided exactly the right conditions for ice to sublimate away. This direct visual confirmation of ice less than 10 centimeters below the surface at Phoenix's location validated the orbital hydrogen measurements and demonstrated that accessible ice exists at shallow depth across vast areas of Mars. Subsequent missions have added detail to the picture of subsurface ice distribution. The Mars Reconnaissance Orbiter's Shallow Radar Instrument, SHARAD, can penetrate deeper than the gamma-ray spectrometer, detecting layers and structures up to a kilometer below the surface. Radar data from SHARAD has revealed ice deposits in many locations, often buried beneath layers of dust and rock that protect the ice from sublimation. These deposits sometimes show distinct layering, suggesting they formed through multiple depositional episodes. In 2018, researchers analyzing SHARAD data reported finding ice at remarkably accessible depths in an area called Utopia Planitia in Mars's northern hemisphere. The ice begins just 1 meter below the surface and extends downward for tens of meters in some locations. The deposit contains enough water ice to fill Lake Superior twice over, making it one of the largest known ice reservoirs outside the polar caps. Crucially, this region lies at relatively low latitude for Mars, between 39 and 49 degrees north, where temperatures are somewhat warmer than in the high polar regions. The formation of these mid-latitude ice deposits connects to the long-term climate cycles driven by changes in Mars' orbital parameters. When Mars's axial tilt increases, the poles receive more direct sunlight and ice sublimates more readily. This water vapor enters the atmosphere and is transported by global circulation patterns toward mid-latitudes, where it deposits as snow during colder periods. Over thousands of years, this process can build up substantial ice deposits at latitudes where ice wouldn't be stable under current conditions. When Mars's tilt later decreases, these deposits become stranded at latitudes where they would normally sublimate away, but if they get covered by a protective layer of dust, they can persist for millions of years. Evidence for past glaciation at mid-latitudes appears in the geomorphology of many Martian landscapes. Features called Lobati debris aprons surround mountains and crater walls in certain latitude bands. These formations, which look like frozen flows of material spreading out from elevated terrain, have been shown by radar measurements to consist largely of ice covered by a thin rocky coating. The ice likely flowed under its own weight in the past, creating glacier-like features that remain today, preserved beneath their dusty mantles. Recent discoveries have revealed ice at even greater depths. In 2024, scientists analyzing seismic data from NASA's InSight lander reported evidence for a vast underground reservoir of liquid water deep within Mars's crust. The InSight mission, which operated from 2018 to 2022, included a seismometer that recorded Marsquakes and meteorite impacts. By analyzing how seismic waves traveled through the planet's interior, researchers could infer properties of the rocks at different depths. The seismic data suggested that rocks at depths of 11.5 to 20 kilometers below the surface are saturated with liquid water trapped in pore spaces and fractures. The amount of water implied by these measurements is staggering, enough to cover the entire planet to a depth of 1 to 2 kilometers if brought to the surface. This would make the deep crustal reservoir the largest known water source on Mars, potentially containing more water than all the surface ice, atmospheric moisture, and shallow subsurface ice combined. The water at these depths remains liquid despite Mars's surface cold, because temperature increases with depth inside any planet due to geothermal heat from the interior. At 10 to 20 kilometers deep in Mars's crust, temperatures are warm enough that water in pores remains liquid rather than frozen, even though this water is under enormous pressure from the rock above it. However, this deep water is effectively inaccessible. Drilling to such depths would be extraordinarily challenging even on Earth, and would be impossible with foreseeable Mars exploration technology. The discovery of deep crustal water helps explain a long-standing mystery about Mars. Geological evidence indicates that the planet once had much more water at its surface, enough to fill an ocean, yet the polar caps and atmosphere contain only a small fraction of that amount. Where did the rest go? Scientists have known that some water was lost to space as Mars's atmosphere escaped over billions of years, but calculations suggested this couldn't account for all the missing water. The deep crustal reservoir provides an answer. A substantial amount of Mars' ancient water didn't escape to space or sublimate into the atmosphere, but instead filtered down into the crust over geological time, where it remains trapped today. The mechanism that moved water into the crust involves chemical weathering of rocks. When water interacts with basaltic rock, which is common on Mars, chemical reactions incorporate water molecules into the crystal structure of clay minerals and other hydrated minerals. This process, called hydration, effectively removes water from the active hydrological cycle and locks it in solid form in rocks. On Earth, plate tectonics recycles crustal rocks back through the mantle, releasing trapped water through volcanic outgassing. Mars lacks active plate tectonics, so once water gets incorporated into crustal rocks, it tends to stay there permanently. Permafrost, ground that remains frozen year-round, likely extends to significant depths beneath much of Mars's surface in regions where subsurface ice exists. On Earth, permafrost forms in Arctic and subarctic regions where ground temperatures stay below freezing. The depth to which permafrost extends depends on surface temperature, geothermal heat flow, and soil properties. But terrestrial permafrost can reach hundreds of meters deep in the coldest regions. On Mars, where surface temperatures are much lower, permafrost could extend several kilometers deep at high latitudes, forming a thick layer of ice-cemented rock and soil. The upper surface of this permafrost, where seasonal temperature variations reach, may experience a cycle of freezing and thawing that creates distinctive surface features. Polygonal patterns visible in many Martian terrains resemble periglacial features on Earth that form through repeated freeze-thaw action. As ice expands and contracts with temperature, it fractures the ground into networks of polygons, each bordered by raised ridges or troughs where ice wedges form. These patterns strongly suggest that Mars's surface layer undergoes ice-related processes even today. The distribution of subsurface ice has important implications for future Mars exploration and potential human presence. Water ice that can be accessed by digging or drilling a meter or two represents a valuable resource. Heating Martian soil to a few hundred degrees Celsius would release water vapor that could be condensed and purified. Electrolysis could then split water into oxygen for breathing and hydrogen for rocket fuel. The energy requirements are significant, but having water available locally eliminates the enormous expense of transporting water from Earth. Several recent studies have identified specific regions on Mars where ice is particularly accessible and where conditions might be suitable for future landing sites. In 2025, researchers reported finding water ice less than 1 meter below the surface in Amazonas Planitia, a region that combines relatively low latitude, flat terrain suitable for landing, and shallow ice. The location strikes a favorable balance between warmer temperatures at lower latitudes and the presence of exploitable ice resources. The possibility that Mars once harbored an ocean has captivated scientists and the public alike since the idea first gained serious consideration in the late 20th century. An ocean on early Mars would have profound implications for the planet's climate history, its potential to support life, and the processes that transformed it from a potentially warm and wet world to the frozen desert we observe today. The evidence for an ancient Martian ocean has grown substantially over decades of observation, though the hypothesis remains a subject of active scientific debate. The story begins with images from the Mariner and Viking missions in the 1970s. These early orbiters revealed dramatic features on Mars' surface that appeared to have been carved by flowing water on a massive scale. Enormous channels, dwarfing Earth's largest rivers, emerged from regions of collapsed terrain and flowed toward the northern lowlands. These outflow channels, as they came to be called, showed characteristics consistent with catastrophic flooding, streamlined islands, scoured bedrock, and converging flow patterns. The northern lowlands of Mars form a vast depression that covers roughly a third of the planet's surface. This region, called Vastitas Borealis, lies 4 to 5 kilometers below the mean planetary elevation, creating a natural basin where any liquid water on Mars would tend to collect. In 1987, researcher John Brandenburg published the hypothesis of a primordial ocean he dubbed Oceanus Borealis, suggesting this northern basin had once been filled with water. Viking images revealed what appeared to be ancient shorelines at 2 distinct elevations in the northern plains, named the Arabia and Deuteronilus shorelines. These features, visible as subtle changes in surface texture and elevation extending for thousands of kilometers, resembled the beach terraces left behind by receding bodies of water on Earth. If genuine shorelines, they would indicate that an ocean had existed at different times or levels during Mars's early history. However, early proposals for Martian shorelines faced significant criticism. Higher resolution topographic mapping in the 1990s showed that the putative shorelines were not level as expected. The Arabia shoreline varied in elevation by several kilometers along its length, rising and falling like hills and valleys rather than maintaining the constant elevation characteristic of a waterline. This irregularity led many scientists to doubt whether these features represented ancient shores at all. The debate over Martian shorelines illustrates a fundamental challenge in planetary science. Features that look like evidence for water from one perspective may have alternative explanations involving volcanic activity, wind erosion, or tectonic processes. Distinguishing between these possibilities requires multiple lines of evidence. Over the past 2 decades, researchers have accumulated such evidence through various approaches, strengthening the case for an ancient northern ocean. One key piece of evidence comes from the radar characteristics of materials in the northern lowlands. In 2012, researchers analyzing data from the Marsis radar on Mars Express reported that subsurface layers in Vastitas Borealis have properties consistent with sedimentary deposits rather than volcanic rock. The radar waves penetrate the surface and reflect differently depending on the material they encounter. The dielectric constant measured in the northern lowlands suggested the presence of low-density sedimentary deposits or massive amounts of ground ice, neither of which would be expected if the region were primarily volcanic. Climate modeling provides another avenue for investigating the ocean hypothesis. In 2022, researchers used sophisticated three-dimensional climate simulations to test whether a liquid ocean could have persisted in Mars's northern hemisphere during the period when geological evidence suggests it existed. Previous models had struggled to explain how an ocean could remain liquid given that Mars was likely receiving less solar energy than Earth during this period and probably had a thinner atmosphere. The new simulations included for the first time a dynamic ocean with realistic circulation patterns. The models showed that ocean currents, driven by temperature and salinity differences, could have prevented the ocean from freezing even when average global temperatures remained below water's freezing point. The circulation would bring warmer water from depth to the surface around the ocean's edges, maintaining a zone of open water despite cold atmospheric conditions. According to these calculations, surface temperatures in the Northern Ocean could have reached 4.5 degrees Celsius, well above freezing, while much of the planet remained locked in ice. Evidence from ancient river deltas adds weight to the ocean hypothesis. Multiple locations around what would have been the shoreline of the proposed ocean show deposits that appear to be deltas, fan-shaped accumulations of sediment where rivers once entered standing water. In 2022, researchers reported finding extensive delta deposits in Aeolis Dorsa, a region east of the proposed ocean basin. They identified over 6,500 kilometers of ridges that represent ancient delta and submarine channel deposits organized into 20 distinct systems. These deposits have characteristics consistent with formation in a large body of standing water rather than isolated lakes. The sedimentary structures indicate that rivers carried sediment into the basin where it accumulated over extended periods. The scale and organization of these deltaic systems suggest they were feeding into a substantial ocean rather than temporary floodwaters. Analysis of the sedimentary architecture revealed features characteristic of environments where rivers meet seas, including backwater zones where flow velocities decrease as rivers enter deep water. Perhaps the most striking evidence for an ancient ocean comes from the discovery of tsunami deposits. In 2016, a large international team of scientists reported finding geological features consistent with two ancient tsunamis in the northern plains. These events would have been triggered by large asteroid impacts into the ocean, creating waves powerful enough to reach 30 meters high and transport boulders the size of cars significant distances inland. The first tsunami left distinct boulder deposits on what would have been the shoreline, with the backwash from the wave-carving channels as water drained back toward the ocean. The second tsunami occurred when the ocean had dropped 300 meters lower, and it carried substantial amounts of ice that remained frozen in Labat deposits at the high water mark. The presence of two tsunamis at different ocean levels suggests the ocean was shrinking between these events, consistent with a planet losing its water over geological time. The composition of Martian meteorites provides independent evidence relevant to the ocean hypothesis. Several meteorites found on Earth are known to have originated from Mars, blasted off the red planet's surface by asteroid impacts and eventually falling to Earth. These rare samples contain minerals that formed in the presence of water. An isotopic analysis of these minerals reveals information about ancient Martian water. Measurements of the deuterium to hydrogen ratio in Martian meteorites show values roughly 2 to 4 times higher than Earth's ocean water. This enrichment in deuterium indicates that Mars has lost substantial water over its history, since hydrogen preferentially escapes to space over the heavier deuterium. The amount of enrichment can be used to estimate how much water Mars once had. These calculations consistently suggest the planet held enough water to cover its surface in a layer 100 to 1,500 meters deep, compatible with an ocean filling the northern basin. Recent discoveries of ancient beach deposits have provided some of the most compelling evidence yet for the ocean hypothesis. In 2025, researchers studying data from China's Zhurong rover, which landed in Utopia Planitia in 2021, reported finding deposits consistent with ancient beaches. Ground-penetrating radar detected layers of sediment with characteristics matching beach sands, including gradual changes in grain size and depositional patterns consistent with wave action. The presence of beach sands implies several things about ancient Mars. First, there must have been a large body of water, since beaches form where waves lap against shores. Second, the water must have been ice-free at the surface, since ice-covered water wouldn't generate the wave action necessary to create beach deposits. Third, there must have been rivers supplying sediment to the beaches, since the sand didn't spontaneously appear, but rather accumulated from erosion of rocks elsewhere on the planet, transported by flowing water. The timeline of the proposed ancient ocean remains a subject of active research. Most evidence suggests the ocean, if it existed, was present during the late Noachian to early Hesperian periods of Martian history, approximately 3.7 to 4.1 billion years ago. This timing corresponds to a period when Mars's magnetic field was weakening or had already disappeared, and when the planet's atmosphere was beginning its long decline through escape to space. The fate of this ancient ocean involves multiple processes. Some water was lost to space as Mars's atmosphere thinned, stripping away both atmospheric gases and water vapor. Some water soaked into the ground, reacting with rocks to form hydrated minerals, effectively locking water into the Martian crust. Some water migrated to the polar regions as the climate cooled, where it remains frozen in the polar caps. The relative importance of these different pathways in removing water from the ocean basin continues to be investigated. The irregular topography of the proposed shorelines, once seen as evidence against the ocean hypothesis, may actually support it when considered in the context of Mars' geological evolution. After an ocean disappeared, the weight of water no longer pressed down on the basin floor. This unloading would have caused the surface to deform over millions of years in a process called isostatic rebound. Additionally, volcanic activity and the planet's slightly elliptical shape would have contributed to vertical movements of the crust. These processes could have tilted and warped the ancient shorelines, creating the elevation variations we observe today. Testing the ocean hypothesis definitively may require future Mars sample return missions or human exploration. Samples from the proposed ocean basin could be analyzed for chemical signatures of marine deposition, such as evaporate minerals that form when seawater evaporates, or biological markers if life existed in the ocean. The presence or absence of such signatures would provide strong evidence for or against the ocean hypothesis. Long before spacecraft reached Mars, telescopic observations revealed dark markings on the planet's surface that some astronomers interpreted as canals, though these turned out to be optical illusions. The real evidence for flowing water on Mars came in 1971 when Mariner 9 entered orbit and returned the first detailed images of the Martian surface. What scientists saw astonished them. Vast networks of valleys, enormous channels carved into bedrock, and features that looked remarkably like dried riverbeds. Valley networks on Mars closely resemble drainage systems on Earth. They consist of main channels with tributaries branching off at acute angles, joining together as they flow downslope in patterns that geologists call dendritic, from the Greek word for tree. These valley networks are concentrated in the ancient southern highlands of Mars, particularly in heavily cratered terrains that date to the planet's first billion years. The valleys cut through the landscape, exposing layered rock in their walls and carrying sediment downstream to form fans and deposits where they reach lower elevations. The valleys vary considerably in size and morphology. Some are long, winding channels with relatively few tributaries, meandering across the landscape like mature rivers. Others form complex multiply-branch networks with countless small tributaries feeding into progressively larger channels. Individual valleys can be tens of kilometers wide and hundreds of kilometers long, though most are smaller. Their depths range from tens to hundreds of meters, with some of the largest valleys cutting more than a kilometer into the surrounding terrain. Understanding how these valleys formed has been central to debates about Mars' early climate. The simplest explanation is that they were carved by flowing water on the surface, just as rivers carve valleys on Earth. This interpretation implies that Mars once had a climate warm and wet enough to support precipitation and runoff, with rain or snowmelt feeding rivers that eroded valleys over extended periods. However, climate models have struggled to produce conditions warm and wet enough for this scenario, leading some researchers to propose alternative formation mechanisms. One alternative hypothesis suggests that many Martian valley networks were carved not by surface rivers fed by precipitation, but by water flowing beneath glacial ice. In 2020, researchers published a detailed study comparing Martian valleys to channels formed beneath glaciers on Earth, particularly in the Canadian Arctic. They found striking similarities in the branching patterns, cross-sectional shapes, and network organization. According to this hypothesis, Mars was cold enough during its early history that water remained frozen as ice sheets at the surface, but basal melting at the bottom of the ice generated flowing water that carved channels in the bedrock below. The glacial hypothesis has important implications. If correct, it suggests that early Mars was cold rather than warm and wet, more similar to Earth during ice ages than during temperate periods. This would be more consistent with the faint young sun paradox, the fact that the sun was about 30% dimmer 4 billion years ago than today, making it difficult to explain how early Mars could have been warm. However, it also suggests that protected environments beneath ice sheets might have provided stable habitats where life could have emerged, shielded from harsh surface conditions. Different types of channels on Mars likely formed through different processes. The valley networks in the southern highlands, with their branching tributary patterns, are most consistent with formation by precipitation-fed surface runoff or subglacial meltwater. In contrast, the enormous outflow channels that emerge from chaos terrain and flow toward the northern lowlands show characteristics of catastrophic flooding. These outflow channels, including systems like Case Valles and Ares Vallis, dwarf Earth's largest rivers. Some are hundreds of kilometers wide and thousands of kilometers long, with depths exceeding 2 kilometers in places. The channels contain streamlined islands, scoured bedrock, and terraces that indicate water levels once stood hundreds of meters high. The volumes of water required to carve these features would have exceeded the combined flow of all Earth's rivers, and the floods likely occurred rapidly in geological terms, possibly over days to weeks rather than the millions of years typical for river erosion. The source of water for these megafloods appears to have been pressurized aquifers deep beneath the Martian surface. The chaos terrain at the heads of many outflow channels consists of collapsed and fractured ground, forming mesas and blocks, suggesting that something was removed from beneath the surface, allowing the overlying rock to collapse. The most plausible explanation is that liquid water trapped in pores and fractures in deep crustal rocks was released catastrophically when something, perhaps volcanic heat, an earthquake, or an asteroid impact, created a pathway for the water to escape. Once released, this water would have erupted onto the frozen Martian surface and flowed downslope toward the northern lowlands. The extreme cold of Mars would have caused ice to form rapidly on the water's surface, but the ice would have acted as an insulating layer, allowing liquid water beneath it to continue flowing for significant periods before freezing solid. Some researchers estimate that these floods could have transported enough water to create temporary seas or lakes in the northern lowlands, though whether these persisted for years, decades, or longer remains uncertain. evidence for ancient lakes appears at multiple scales across Mars. At the small scale, many craters in the southern highlands contain deposits consistent with lake sediments. Orbital spectroscopy reveals clay minerals within these deposits, formed through chemical weathering in the presence of water. At larger scales, closed basins show evidence of past lake levels, with terraces marking former shorelines and channels that connected one lake basin to another, allowing overflow when one filled beyond capacity. In 2025, researchers reported new evidence for wave ripples preserved in ancient Martian sediments. NASA's Curiosity rover photographed rock formations in Gale Crater, showing distinctive ripple patterns that could only have formed underwater in the presence of wind-driven waves. These ripples have wavelengths and shapes characteristic of shallow water environments open to the atmosphere, where wind generates waves that interact with the sediment bed. The discovery provides some of the strongest evidence yet that ancient Mars had liquid water bodies with free surfaces exposed to the air. The age of valley networks can be estimated through crater counting. When a surface is young with few craters, it means impacts haven't had much time to accumulate since the surface formed. Heavily cratered surfaces are ancient, having been exposed to bombardment over billions of years. By counting craters superimposed on valley networks and the surrounding terrain, scientists can estimate when the valleys were active. Most valley networks date to the late Noachian period, roughly 3.7 to 3.9 billion years ago, though some appear older and others younger. The discovery that valley formation was concentrated in Mars's first billion years raises questions about why conditions favorable for valley formation didn't persist. Several factors probably contributed to the transition. Mars is smaller than Earth, with a radius about half as large, and small planets cool more rapidly because they have more surface area relative to their volume. As Mars cooled, volcanic activity declined, reducing the outgassing of greenhouse gases that might have kept the atmosphere thick and warm. Additionally, Mars's weak magnetic field, or lack thereof, meant the solar wind could strip away atmospheric gases more readily than on Earth, where a strong magnetic field deflects the solar wind. Recent discoveries suggest water activity on Mars didn't end completely 3 billion years ago. Some valley networks appear to have formed more recently, within the past 3 billion years. In 2019, researchers reported evidence for intense, climate-driven runoff that persisted late in Mars's history, possibly as recently as 2 billion years ago. These findings suggest that Mars experienced episodic periods of wetter conditions even after its overall climate transitioned to the cold, dry state we observe today. Deltas at the mouths of valleys provide particularly detailed records of ancient water activity. A delta forms when a river enters a standing body of water, causing the flow velocity to decrease and sediment to deposit. The Jezero crater, landing site of the Perseverance rover, contains a well-preserved delta where sediment accumulated as a river emptied into a crater lake. The rover is currently exploring this delta, analyzing its layers and composition to understand what the lake environment was like and whether it could have supported life. The mineralogy of sediments in valley networks and their deposits provides information about water chemistry. Clay minerals, detected by orbital spectrometers, indicate that water was present long enough and at appropriate pH and temperature for these minerals to form. The specific types of clays reveal conditions of formation. For example, iron-magnesium smectite clays typically form in neutral to slightly alkaline water, suggesting the water in some Martian valleys wasn't strongly acidic. The atmosphere of Mars holds only trace amounts of water at any given time, yet the water that does exist there plays an important role in the planet's current climate and provides valuable information about water cycling between different reservoirs. Measuring atmospheric water vapor has been a goal of Mars missions since the earliest orbiters, and the picture that has emerged reveals a dynamic system of seasonal and diurnal variations driven by temperature, pressure, and circulation patterns. The total amount of water vapor in Mars's atmosphere is tiny by Earth standards. If all the atmospheric water vapor on Mars were condensed into liquid and spread evenly across the planet's surface, it would form a layer just 10 to 20 micrometers thick, about the thickness of a human hair. For comparison, Earth's atmosphere contains enough water vapor to cover the surface in about 25 millimeters of liquid water, if condensed, roughly 1,000 times more than Mars. Despite this scarcity, atmospheric water on Mars exhibits strong seasonal and spatial patterns. The primary driver of these patterns is sublimation from the North Polar ice cap during northern summer. As temperatures rise above the frost point at high northern latitudes, water ice sublimates directly from the polar cap into the atmosphere. This creates an annual peak in atmospheric water content at northern latitudes during local summer, with column abundances reaching up to 80 precipitable micrometers, the equivalent of an 80 micrometer thick layer of liquid water if all moisture in an atmospheric column were condensed. The water vapor released from the North Polar Cap doesn't stay localized. Global atmospheric circulation patterns transport it to other regions of the planet. During northern summer, water vapor spreads southward and accumulates at high southern latitudes, where some of it deposits as frost. The process reverses during southern summer, though with significantly lower amplitude because the South Polar Cap is smaller and contains less accessible surface ice than the North Polar Cap. Temperature exerts fundamental control over atmospheric water content. Colder air can hold less water vapor before reaching saturation and forming ice crystals or frost. The relationship between temperature and saturation vapor pressure means that even Mars's small atmospheric temperature changes produce large relative changes in the air's capacity to hold moisture. This effect is particularly pronounced during the diurnal cycle. During Martian days, surface temperatures can climb well above freezing at low latitudes, especially during summer. As the surface warms, water vapor can accumulate in the near-surface air, subliming from frost deposits or desorbing from soil particles. However, the air remains far from saturated during these warm periods. Relative humidity typically stays near 0% during the day. As evening approaches and temperatures drop, the air cools rapidly and relative humidity rises, even though the absolute amount of water vapor hasn't changed much. By the coldest hours before dawn, relative humidity can exceed 60% at some locations. The Curiosity rover has made detailed measurements of this diurnal humidity cycle at Gale Crater since landing in 2012. The rover's environmental monitoring station includes sensors that measure both air temperature and relative humidity. Over multiple Martian years of observation, a clear pattern has emerged. Humidity peaks just before dawn when temperatures reach their daily minimum, then drops to near 0% shortly after sunrise. This cycle repeats daily, though the magnitude varies seasonally with higher peak humidity values. During winter months, when overall temperatures are lower, these daily humidity cycles have implications for whether liquid water might briefly exist on Mars. The combination of relatively high humidity and temperatures near or above freezing, a condition that sometimes occurs for brief periods around dawn, creates conditions where certain salts could potentially absorb atmospheric moisture and form liquid brines through a process called deliquescence. However, the time windows where both temperature and humidity are favorable rarely exceed an hour or two, raising questions about whether deliquescence actually occurs or if kinetic limitations prevent it. Frost formation is a regular occurrence at high latitudes and in some equatorial locations during cold seasons. The Viking 2 lander, which touched down at about 48 degrees north latitude, directly observed thin layers of water ice frost forming on the ground during winter. The frost appeared as a white coating in images taken by the lander's cameras and persisted for several months before sublimating away as spring arrived. The Phoenix lander similarly observed frost formation at its landing site near the North Polar region. Even at equatorial latitudes, frost can form under specific conditions. The Mars Exploration Rover Opportunity, operating near the equator, detected small amounts of frost on its calibration targets on cold winter mornings. These extremely small frost deposits formed when radiative cooling at night lowered surface temperatures below the atmospheric dew point, allowing ice crystals to condense directly from the moisture in the air. The frost typically sublimated within an hour of sunrise. Recent studies using data from Mars orbiters have detected widespread diurnal frost formation at low latitudes, including areas close to the equator. High-resolution thermal infrared observations revealed that small, localized cold spots appear on crater floors and shaded slopes just before dawn, where temperatures dip low enough for frost to condense. These frost deposits are ephemeral, lasting only until sunrise, but their widespread occurrence demonstrates that atmospheric moisture regularly deposits on the surface and re-enters the atmosphere in daily cycles even near the equator. The vertical distribution of water vapor in Mars's atmosphere shows interesting patterns. Generally, water vapor concentrations are highest near the surface and decrease with altitude. However, the atmosphere isn't well mixed for water vapor as it is for most other gases. During northern summer, when water sublimes rapidly from the polar cap, substantial amounts of water vapor reach high altitudes where ultraviolet radiation from the sun can break water molecules apart into hydrogen and oxygen atoms. This photodissociation in the upper atmosphere contributes to Mars losing water to space over geological time. Seasonal variations in atmospheric water vapor have been tracked by multiple missions over more than 4 decades. The Viking orbiters in the 1970s provided the first systematic monitoring of water vapor. These measurements revealed the basic seasonal pattern: an annual maximum at high northern latitudes during northern summer, and a secondary smaller peak at high southern latitudes during southern summer. Every subsequent mission with water vapor monitoring capability has confirmed and refined this picture. Clouds form regularly in Mars' atmosphere, and many of these clouds consist of water ice crystals rather than carbon dioxide ice. Water ice clouds appear frequently over the Tharsis volcanic region, where topography forces air upward, causing adiabatic cooling that allows moisture to condense. The so-called aphelion cloud belt, a band of clouds that forms at tropical latitudes during Mars' aphelic season when the planet is farthest from the Sun, consists largely of water ice crystals. These clouds can extend hundreds of kilometers and persist for weeks or months. The presence of water ice clouds demonstrates that the Martian atmosphere regularly reaches saturation with respect to water despite its overall dryness. Cloud formation requires not just sufficient humidity, but also condensation nuclei, tiny particles around which ice crystals can form. On Mars, dust particles serve this role. Dust is ubiquitous in the Martian atmosphere, periodically lifted by strong winds or dust storms, and provides abundant surfaces where water molecules can aggregate and freeze. The story of where Mars's water went is written not in the substance itself, but in the ratio of its isotopes. Hydrogen exists in 2 stable forms: ordinary hydrogen with 1 proton in its nucleus, and deuterium, also called heavy hydrogen, which has both a proton and a neutron. Water molecules can be made from either isotope, producing either normal H2O or the heavier HDO, where 1 hydrogen is replaced by deuterium. The ratio between these 2 forms tells a powerful story about how much water Mars has lost over its history. On Earth, about 1 in every 6,500 hydrogen atoms in ocean water is deuterium, giving a DH ratio of approximately 1.55 times 10 to the minus 4. This value, called Standard Mean Ocean Water, or SMAO, serves as a reference point for comparing other solar system bodies. When scientists first measured the DH ratio in Martian water, they found it substantially enriched in deuterium compared to Earth's oceans, with values ranging from 5 to 8 times the terrestrial ratio. This enrichment reveals that Mars has lost a large fraction of its original water. The physical basis for this interpretation is straightforward. Hydrogen and deuterium atoms escape from the top of Mars' atmosphere at different rates. Because deuterium atoms are twice as massive as hydrogen atoms, they move more slowly at any given temperature. When atmospheric gases escape to space, the lighter hydrogen atoms escape preferentially, gradually enriching the remaining water in the heavier deuterium isotope. The preferential escape of hydrogen over deuterium is well understood from fundamental physics. At the top of Mars' atmosphere, gas molecules and atoms move in random thermal motion with speeds that follow a statistical distribution called the Maxwell-Boltzmann distribution. A small fraction of particles have speeds exceeding the planet's escape velocity and can leave the atmosphere permanently. For hydrogen atoms, this escape speed threshold is lower than for deuterium atoms due to their lower mass, so hydrogen escapes more readily. Multiple techniques have been used to measure the DH ratio on Mars. Ground-based telescopes using infrared spectroscopy first detected deuterium enrichment in the 1980s by comparing absorption lines from HDO and H2O in reflected sunlight from Mars. Spacecraft instruments have since provided much more detailed measurements. The Mars Express orbiter has mapped DH ratios across the planet and through different seasons. The Curiosity rover has measured deuterium in water released from rocks it drilled. The measurements reveal interesting spatial and temporal variations. Water vapor at low altitudes shows enrichment values close to the 4 to 8 times Earth's ratio, but measurements of escaping hydrogen atoms in the upper atmosphere reveal deuterium fractionation occurring in real time. The MAVEN spacecraft has measured the DH ratio in atomic hydrogen escaping from Mars' upper atmosphere and found values that indicate lighter hydrogen escapes preferentially, just as theory predicts. Calculating how much water Mars has lost based on deuterium enrichment requires making assumptions about the initial DH ratio. If we assume Mars started with water similar to Earth's ocean water, with DH around 1.5 times 10 to the -4, and the current Martian value is about 8 times higher, this enrichment implies Mars has lost about 87% of its original water. However, this calculation depends sensitively on the fractionation factor, which describes how much more readily hydrogen escapes compared to deuterium. The fractionation factor itself is not constant but depends on the physical processes driving escape. During thermal escape, where atoms have enough thermal energy to reach escape velocity, the fractionation factor can be quite high, around 100, meaning hydrogen escapes 100 times more readily than deuterium. For non-thermal escape processes, where atoms gain energy through chemical reactions or interactions with ions and charged particles, the fractionation factor is typically lower, perhaps 5 to 20. The actual fractionation depends on which processes dominate at any given time. Recent studies combining DH measurements with models of atmospheric escape have refined estimates of Mars's primordial water inventory. One estimate suggests Mars once held enough water to cover the planet in a layer 630 meters deep, though uncertainty ranges from about 30 meters to 1 kilometer. For comparison, if Earth's oceans were spread evenly over the entire planet's surface, they would form a layer about 2,700 meters deep. So Mars's ancient water inventory, while substantial, was likely smaller than Earth's current oceans. Not all of Mars's missing water escaped to space. A significant fraction became incorporated into the planet's crust through chemical weathering. When water interacts with volcanic rock, particularly basalt, which is common on Mars, it forms hydrated minerals like clays. These minerals contain water molecules or hydroxyl groups bonded into their crystal structure. A 2021 study estimated that chemical weathering has sequestered water equivalent to a global layer between 300 and 1,500 meters deep in the Martian's crust. This crustal sequestration provides an alternative explanation for where Mars's water went. Instead of escaping to space or remaining frozen at the poles, much of it reacted with rocks and became permanently locked underground. The authors of the crustal sequestration study suggested this process may have been the dominant sink for water during Mars's transition from wet to dry, potentially more important than atmospheric escape for the total water budget. The timing of water loss from Mars connects to the planet's magnetic field history. Mars once had a global magnetic field generated by a liquid iron core, similar to Earth's magnetic field today. This magnetic field would have shielded the atmosphere from the solar wind, reducing atmospheric escape. However, Mars's magnetic field disappeared about 4 billion years ago when the core cooled and stopped generating the magnetic dynamo. Without this protective shield, the solar wind could directly interact with Mars's upper atmosphere, stripping away gases more readily. The MAVEN mission has directly measured how the solar wind removes atmospheric gases from Mars today. Ion pickup, a process where solar wind strips away ionized atmospheric particles, currently removes about 100 grams of atmosphere per second. Scaled over billions of years, this process alone could have removed enough atmosphere to account for Mars's thin air today. The loss of atmospheric pressure would have made liquid water unstable on the surface, driving further water loss through sublimation and escape. Mars's elliptical orbit affects water loss rates in measurable ways. The planet's distance from the Sun varies by about 40 million kilometers over the course of its year, with perihelion occurring during southern summer. At perihelion, Mars receives about 45% more solar energy than at aphelion. This increased heating has multiple effects on water. It warms the polar caps, increasing sublimation. It lifts water vapor to higher altitudes. And it increases the rate at which solar ultraviolet radiation breaks water molecules apart, generating atomic hydrogen that can escape. MAVEN observations have shown that hydrogen escape rates vary by a factor of 10 between Mars's closest and farthest points from the Sun. At perihelion, during southern summer, escape rates reach about 3 times 10 to the 27th atoms per second. At aphelion, during northern summer, rates drop to about 3 times 10 to the 26th atoms per second. These variations occur every Martian year, creating episodic rather than steady water loss. Global dust storms dramatically enhance water loss. During the 2018 global dust storm, the largest observed in decades, water vapor was lofted to unprecedented altitudes in the Martian atmosphere. Measurements showed water reaching altitudes above 80 kilometers, where it is normally very rare. At these heights, ultraviolet radiation quickly broke the water molecules apart, and the resulting hydrogen atoms escaped efficiently. The dust storm effectively short-circuited the normal cold trap that keeps water at lower altitudes, allowing enhanced escape for several months. The cumulative effect of these periodic enhancements in water loss may have significantly affected Mars's long-term water budget. If global dust storms occur every few years or decades, and if Mars's orbital parameters undergo cycles that increase perihelion heating every few million years, these episodic events could drive substantial water loss over geological time, even though present-day base rates seem modest. Looking forward, scientists hope to refine estimates of water loss by combining measurements from multiple missions. The ExoMars Trace Gas Orbiter, operated by the European Space Agency, is measuring water vapor distribution with high vertical resolution, providing crucial data on how water reaches the upper atmosphere. MAVEN continues monitoring hydrogen escape and atmospheric conditions. The Emirates Mars Mission Hope Orbiter is providing global context on atmospheric dynamics. Together, these missions are building a comprehensive picture of Mars's present-day water cycle and loss processes. The Phoenix Mars lander made a remarkable discovery in 2008 when it dug shallow trenches near Mars's North Polar region. Chemical analysis of the soil revealed high concentrations of perchlorate salts, compounds containing chlorine and oxygen in a particular molecular arrangement. Perchlorates are hygroscopic, meaning they readily absorb water vapor from the air, and they dramatically lower the freezing point of water. The presence of perchlorate salts raises the intriguing possibility that liquid brines might form on Mars today, despite conditions that would normally keep water frozen or cause it to sublimate. Perchlorates exist in Martian soil at concentrations around 0.5 to 1% by mass based on measurements from multiple landing sites. The Phoenix lander measured concentrations near 1%. The Curiosity rover found similar values at Gale Crater near the equator, indicating perchlorates are widespread rather than localized. These salts likely formed through atmospheric chemical reactions involving chlorine and oxidants, then deposited onto the surface over millions of years of Mars history. The chemical properties of perchlorate solutions make them particularly interesting for Mars. Pure water freezes at 0 degrees Celsius, but dissolving salts lowers the freezing point through a process called freezing point depression. Concentrated perchlorate brines can remain liquid down to -70 degrees Celsius, or even lower depending on the specific salt and concentration. Since Mars's surface temperatures regularly exceed -70 degrees during spring and summer at many latitudes, conditions theoretically allow for liquid perchlorate brines. Deliquescence provides a mechanism for brines to form even when no liquid water is initially present. Hygroscopic salts can absorb water vapor directly from the atmosphere when relative humidity exceeds a threshold value called the deliquescence relative humidity. For perchlorate salts at Martian temperatures, this threshold is around 70 to 80% relative humidity. When humidity exceeds this level, the salts absorb enough atmospheric moisture to dissolve completely, forming liquid brine droplets. The Phoenix lander observed suggestive evidence for this process. Images from the lander's robotic arm camera showed what appeared to be small droplets, or beads, forming on the spacecraft's legs during the mission. These features appeared after the soil was disturbed, growing over several Martian days before eventually disappearing. Mission scientists proposed that perchlorate salts were splashed onto the lander legs when the retro rockets blew soil around during landing. As temperature and humidity conditions varied through the day-night cycle, these salts could have absorbed atmospheric moisture and formed tiny brine droplets. The timing of when brines might form depends on the intersection of temperature and humidity requirements. For deliquescence to occur, both temperature must be warm enough that the brine doesn't freeze, and humidity must be high enough to exceed the deliquescence threshold. These conditions rarely occur simultaneously on Mars. During the day, temperatures may be warm enough, but relative humidity is typically very low. At night, humidity rises as air cools, but temperatures often drop below the brine's freezing point. Laboratory experiments have explored under what conditions Martian brines can form and persist. Researchers created chambers that simulate Martian atmospheric pressure, temperature cycles, and humidity, then introduced perchlorate salts to see if brines would form. These experiments confirmed that deliquescence can occur under Mars-like conditions, but the time windows are brief, typically lasting an hour or two around dawn when temperatures rise above the brine freezing point, but humidity remains elevated from the cold night. The implications for liquid water availability on present-day Mars depend on how we define available water. If we mean substantial quantities that could support biological activity, the evidence suggests liquid water is extremely rare or absent. The hypothetical brine films would be microscopic, highly concentrated with salt, and ephemeral, existing for at most a few hours before either freezing or evaporating. These conditions fall outside the range where terrestrial life operates, even for extremophiles adapted to salty environments. However, even transient brines could have geological significance. Liquid water, even in small amounts, can facilitate chemical reactions, cause grains to cement together, or enable small amounts of erosion or deposition. Some researchers have proposed that brines might contribute to forming certain surface features observed on Mars, though this remains controversial and debated. Recurring slope lineae, or RSL, have been one of the most debated potential indicators of modern liquid water on Mars. These dark streaks appear on steep slopes during warm seasons, gradually extending downhill over weeks to months, then fading when temperatures cool. When RSL were first reported in 2011, they immediately sparked interest as potential signs of briny water flows. Several characteristics of RSL seemed consistent with liquid water. They appear only when and where temperatures exceed the freezing point of perchlorate brines. They occur on sun-facing slopes that receive maximum solar heating. They extend downslope in patterns resembling seepage or flow. They recur year after year in the same locations, suggesting an ongoing process rather than a one-time event. Thousands of individual RSL have been identified across more than 50 sites on Mars, from near the equator to mid-latitudes. Spectroscopic analysis added to the intrigue. In 2015, scientists reported detecting hydrated salts in RSL using the CRISM instrument on Mars Reconnaissance Orbiter. The spectra showed absorption features consistent with perchlorates and other magnesium and calcium salts in a hydrated state, meaning they contained water molecules. The presence of hydrated salts where RSL are active seemed to support the idea that brines were involved in their formation. However, subsequent investigations have cast doubt on the liquid water interpretation. Detailed topographic analysis published in 2017 showed that RSL end at slopes that match the angle of repose for dry sand, about 30 to 35 degrees. If liquid flows were creating the streaks, they should be able to flow onto shallower slopes, as water on Earth readily does. The fact that RSL stop at precisely the slope angle where dry granular flows stop suggests they might be dry avalanches or grain flows rather than wet features. Other observations also challenge the brine hypothesis. The total length of RSL scales with the extent of steep slopes available, not with proximity to water sources. If underground water were feeding RSL, we would expect longer features near water reservoirs and shorter ones farther away. But this pattern is not observed. Additionally, the amount of water required to explain the darkening, if brines were responsible, exceeds what the atmosphere could plausibly supply through deliquescence. An alternative explanation proposes that RSL form through seasonal flows of dry sand triggered by small amounts of subsurface moisture. In this model, ice or salts beneath the surface undergo phase changes as seasons progress. These phase changes could destabilize sand grains, causing them to flow downslope. The resulting grain flows would darken the surface by removing bright dust and exposing darker underlying material. Small amounts of moisture might be involved in the triggering mechanism without requiring liquid flows on the surface. The presence of hydrated salts, which initially seemed to support liquid water, might have an alternative explanation. Salts in Martian soil are ubiquitous and can become hydrated by absorbing atmospheric moisture without requiring bulk liquid water. The hydration might occur through repeated cycles of atmospheric moisture absorption rather than through interaction with liquid brines. Additionally, the spectral signatures of hydrated salts appear both where RSL are active and in surrounding terrain, suggesting the salts exist throughout the region rather than being unique to RSL. The debate over RSL interpretation highlights a broader challenge in Mars science, distinguishing between processes that require liquid water and those that can occur in dry conditions but might involve small amounts of moisture or ice. Many Martian surface features could plausibly form through multiple mechanisms, and determining which actually operated requires careful analysis of multiple lines of evidence. Frost formation represents another context where water transitions between solid and vapor phases on present-day Mars. Water ice frost deposits regularly on the surface at high latitudes and occasionally at low latitudes during cold seasons. These frost deposits form when water vapor in the atmosphere condenses directly as ice crystals on the cold ground surface, similar to how frost forms on Earth, but without passing through a liquid phase. The amount of frost that forms varies by location and season. At the Phoenix landing site near 70 degrees north latitude, frost appeared regularly during late autumn and winter, sometimes accumulating to depths of a few millimeters. The frost persisted for months before sublimating away as spring progressed and sunlight returned. Even at the equator, small amounts of frost can form in sheltered locations during the coldest part of winter nights. observations have detected frost formation on a daily cycle in some locations. Before dawn, when surface temperatures reach their daily minimum, thin layers of frost condense from moisture in the near-surface air. This frost sublimates within an hour or two after sunrise as sunlight warms the surface. These daily frost cycles demonstrate that Mars's atmosphere and surface exchange water constantly through sublimation and condensation, even though the total amount of water involved is small. The role of salts in enhancing frost stability has been investigated through experiments and observations. Salts can absorb water vapor and form hydrated minerals at temperatures and pressures where pure water ice would sublimate away. This means salt-rich soils might maintain more moisture than salt-free soils under identical atmospheric conditions. However, whether this process occurs to a significant extent in natural Martians environments remains uncertain. Laboratory studies have examined what happens when perchlorate brines freeze and thaw repeatedly under Martian conditions. The freeze-thaw cycles cause the brine to concentrate as ice freezes out, leaving behind progressively saltier liquid. This can lead to the formation of crystalline salts interlayered with ice. Such mixtures might be more stable than pure ice under Mars surface conditions. Additionally, the freeze-thaw process can alter soil structure, creating patterns of polygons, mounds, and cracks similar to those observed in Martian polar regions. When NASA selected Gale Crater as the landing site for the Curiosity rover in 2012, the choice was driven by evidence that this 150-kilometer-wide crater once contained a lake billions of years ago. The crater's central peak, Mount Sharp, rises about 5,000 meters above the crater floor and consists of layered sedimentary rocks that likely formed from sediments deposited in standing water. Orbital observations had shown that these rocks contain clay minerals and sulfate minerals, both of which form in aqueous environments, making Gale an ideal location to investigate Mars' ancient habitability. Curiosity landed on the crater floor in a region called Bradbury Landing and began its traverse toward the base of Mount Sharp. During the first few months, the rover crossed relatively flat terrain with occasional outcrops of rock exposed through the wind-eroded dust. When Curiosity reached a location named Yellowknife Bay, about 500 meters from the landing site, the mission team made a crucial decision to stop and investigate an area of exposed bedrock. Yellowknife Bay contained fine-grained sedimentary rock called mudstone, darker and smoother than the surrounding terrain. Curiosity drilled into this mudstone to collect powder samples for analysis by the rover's onboard chemistry labs. The results revealed an environment that would have been habitable for microbial life if such life ever existed on Mars. The mudstone contained clay minerals, sulfate minerals, and other compounds indicating it formed in fresh water with near-neutral pH and low salinity. The mineralogical composition told a detailed story about ancient conditions. X-ray diffraction analysis showed the rock contained smectite clays, which form when basaltic rock weathers in water over extended periods. The presence of specific types of clays indicated the water was relatively fresh, not highly acidic or salty. Additionally, the analysis detected minerals like magnetite and sulfides that form in reducing environments where oxygen is scarce, contrasting with the heavily oxidized surface conditions that characterize modern Mars. Chemical analysis revealed the rock contained the essential elements for life: carbon, hydrogen, oxygen, nitrogen, sulfur, and phosphorus, often remembered by the acronym CHNOPS. While the presence of these elements doesn't prove life existed, it demonstrates the ancient environment had all the chemical building blocks life would have required. The nitrogen appeared primarily in nitrate minerals, suggesting complex chemical reactions had processed nitrogen in the aqueous environment. The physical structure of the mudstone provided information about depositional conditions. The fine grain size, with particle diameters mostly less than 50 micrometers, indicated the sediment settled slowly from still or slow-moving water. Had the water been flowing rapidly, it would have transported and deposited coarser sand and gravel rather than fine mud. The mudstone also showed sedimentary features like crossbedding and layers with varying grain sizes, suggesting water levels and flow conditions changed over time. Curiosity's traverse toward Mount Sharp took it through varied terrain that told different chapters of Gale Crater's history. After leaving Yellowknife Bay, the rover crossed areas with rocks showing different degrees of weathering and cementation. Some locations contained conglomerate rocks with rounded pebbles, indicating flowing water energetic enough to transport rocks the size of golf balls or larger. Other locations showed fine layering suggestive of sediment settling in calm water. When Curiosity reached the base of Mount Sharp at a formation named Murray Formation, the rover began ascending through layers that represent sequential deposits spanning millions of years. The Murray Formation consists primarily of mudstone, similar to what Curiosity found at Yellowknife Bay, suggesting lake conditions persisted for an extended period. As the rover climbed higher, it encountered rocks with increasing amounts of sulfate minerals, suggesting the lake chemistry changed over time, potentially becoming more acidic or experiencing episodes of evaporation. The presence of hematite concretions, small spherical nodules of iron oxide embedded in the mudstone, provided additional clues about water chemistry. These concretions form when iron-bearing minerals dissolve in groundwater and later precipitate in concentrated zones within the rock. Their presence indicates water continued to percolate through the sediment even after initial deposition, potentially for millions of years after the lake dried. Orbital observations combined with rover measurements have allowed scientists to reconstruct the lake's history. During the Noachian period, roughly 3.6 to 3.8 billion years ago, Gale Crater filled with water entering through channels that breached the northern rim. The lake reached depths estimated at tens to perhaps 100 meters based on the elevation of deposits and the crater rim morphology. The lake fluctuated in extent and depth over time as climate conditions varied. Sediment entering the lake from surrounding highlands settled on the lake floor, gradually building up layers of mudstone. The central peak of the crater, Mount Sharp, began forming from these sediments, though the exact mechanism remains debated. One hypothesis suggests wind erosion removed sediment from the crater while leaving deposits around the center, gradually sculpting the mountain. Another suggests that Mount Sharp formed through sediment deposition, building up over millions of years without requiring extensive erosion. The duration that liquid water persisted in Gale Crater has important implications for habitability. For life to establish itself, environments typically need to remain stable for extended periods, at least tens of thousands to millions of years. The thick sequence of mudstone deposits suggests the lake existed intermittently or continuously for perhaps 100,000 to 10 million years or longer, potentially long enough for life to have emerged if other conditions were favorable. Organic molecules, the carbon-containing compounds that form the basis of life, have been detected in several samples drilled by Curiosity. In 2018, mission scientists reported finding complex organic compounds in mudstone samples. These included thiophenies, benzene, toluene, and small carbon chains. Importantly, these organics were found in multiple samples from different locations and rock layers, indicating their presence is not a one-time occurrence, but represents widespread organic matter preservation. The origin of these organic compounds remains uncertain. They could be remnants of ancient Martian life, though this is considered less likely. More probably, they formed through non-biological chemical reactions, either on Mars or arrived via meteorites. Organic compounds are delivered to planetary surfaces continuously through meteorite and interplanetary dust, particle infall. Some organic molecules may have formed on Mars through chemical reactions between atmospheric gases and minerals in the presence of water, or through reduction of atmospheric carbon dioxide by minerals. The fact that organics are preserved in Gale Crater rocks is itself significant. Mars's surface is hostile to organic preservation due to intense ultraviolet radiation and highly oxidizing soil chemistry. Organic molecules at the surface should be destroyed relatively quickly within perhaps 100 million years. Their preservation in mudstone samples that Curiosity drilled from beneath the surface indicates the subsurface provides protection from degradation processes. This suggests that if biosignatures of ancient life exist on Mars, they would most likely be found in subsurface rock samples. Curiosity has also detected methane in Gale Crater's atmosphere, another finding with implications for water and potential habitability. Methane measurements have shown low background levels around 0.5 parts per billion by volume, with occasional spikes to several parts per billion. Methane is interesting because it is destroyed by photochemistry in Mars' atmosphere, with a lifetime of a few hundred years, so any methane detected today must have been released relatively recently from subsurface sources. The source of Martian methane is debated. On Earth, most atmospheric methane comes from biological activity, but significant amounts are also produced through geological processes like serpentinization, where water reacts with iron-rich minerals in subsurface rocks, releasing methane as a byproduct. On Mars, the methane could come from either ancient organic matter being released from rocks as they erode and crack, or from active geological processes involving subsurface water. The sporadic nature of methane detections suggests it is released in episodic bursts rather than continuously. This could result from seasonal processes like thermal expansion and contraction of rocks that open and close pathways for gas release, or from changes in subsurface pressure as ice melts and refreezes with seasonal temperature variations. Understanding the methane cycle would benefit from having a dense network of atmospheric monitoring stations across Mars, which future missions might provide. Recent drilling campaigns have targeted different types of rocks to understand the full range of ancient environments. Curiosity has drilled into sulfate-bearing rocks higher on Mount Sharp, where conditions likely transitioned toward drier, more acidic environments as the climate evolved. These rocks still preserve evidence of water, but represent different chemical conditions than the earlier freshwater lake deposits. The rover has documented multiple generations of groundwater activity recorded in rock textures and mineral veins. Light-colored veins cutting through mudstone indicate that minerals precipitated from groundwater that percolated through fractures in the rock long after the lake dried. Chemical analysis shows these veins contain calcium sulfate, indicating they formed from relatively salty water. The presence of these veins at various elevations on Mount Sharp indicates groundwater remained active in Gale Crater's subsurface for millions of years after surface water disappeared. Water on Mars exists not only as ice and vapor, but also bound into the crystal structure of minerals. These hydrated minerals, which contain water molecules or hydroxyl groups as part of their chemical composition, provide long-term stable storage for water that persists even under Mars' dry surface conditions. Understanding the distribution and abundance of hydrated minerals helps constrain Mars's total water budget and reveals where water was available in the past. Clay minerals represent one of the most important classes of hydrated minerals on Mars. Clays form when igneous rocks, particularly basalts, undergo chemical weathering in the presence of liquid water over extended periods. The process, called aqueous alteration, breaks down minerals like olivine and pyroxene that crystallized from magma, converting them into clay minerals that incorporate water into their structure. The specific types of clays that form depend on the pH, temperature, and chemistry of the water involved. Orbital spectroscopy has mapped clay mineral deposits across broad regions of Mars' ancient southern highlands. The CRISM instrument on Mars Reconnaissance Orbiter can identify mineral types by analyzing how sunlight reflects off the surface at hundreds of different wavelengths. Clay-rich regions appear in scattered outcrops within impact crater walls, valley networks, and layered deposits, particularly in terrains dating to the Noachian period. Phyllosilicate clays, which include minerals like montmorillonite, nontronite, and saponite, are detected most commonly. These clays contain roughly 10 to 15% water by mass bound in their crystal structure. In some clay-rich deposits, water content may reach 20% or more. Given that clay deposits have been detected across hundreds of thousands of square kilometers, the total amount of water stored in clays in Mars's upper crust could be substantial, potentially equivalent to tens of meters of water spread globally. The formation of extensive clay deposits requires significant amounts of liquid water and time. On Earth, clays typically form over tens of thousands to millions of years as rocks weather in the presence of rainwater, groundwater, or standing water. The presence of thick clay-bearing units on Mars, sometimes hundreds of meters deep, indicates sustained aqueous activity. This evidence strongly supports the hypothesis that early Mars had a more active hydrological cycle with surface and subsurface water present for geologically significant periods. Different clay minerals form under different environmental conditions, allowing scientists to infer properties of ancient Martian water. Iron-magnesium smectite clays typically form in neutral to slightly alkaline water with moderate temperatures, conditions favorable for habitability. In contrast, certain aluminum-rich clays form in more acidic conditions. By mapping which types of clays occur in specific locations and layers, researchers can reconstruct how water chemistry varied across Mars and how it changed over time. Sulfate minerals represent another major class of hydrated minerals abundant on Mars. Sulfates form when rocks weather in the presence of acidic water, often water enriched in sulfuric acid. Gypsum, a calcium sulfate containing about 20% water by mass, is particularly common. Other sulfates include kieserite, epsomite, and jarosite. Sulfate deposits are especially prominent in layered formations in the Valles Marineris canyon system and in deposits near the polar regions. The transition from clay-rich deposits in the oldest terrains to sulfate-rich deposits in younger formations suggests Mars water chemistry changed over time. This transition might reflect changes in volcanic outgassing, atmospheric composition, or the degree of water-rock interaction. Some researchers interpret the clay-to-sulfate transition as indicating that early Mars had relatively fresh, neutral water that gradually became more acidic, possibly as sulfur dioxide from volcanic eruptions dissolved in water to form sulfuric acid. Hydrated silica, or opal, has been detected in several locations on Mars. Opal forms when silica-rich water precipitates the mineral in hot springs, near volcanic vents, or in certain weathering environments. The presence of opal can indicate hydrothermal activity, where water heated by volcanic or impact-related thermal energy dissolved silica from rocks and later deposited it. Hydrothermal systems are of particular interest for astrobiology because on Earth they often harbor diverse microbial communities. Carbonates, which could store large amounts of carbon dioxide in addition to water through chemical weathering, have been found but are surprisingly scarce on Mars. Early in Mars's history, if the planet had a thick carbon dioxide atmosphere and liquid water on its surface, chemical reactions should have produced substantial carbonate deposits as carbon dioxide dissolved in water and reacted with rocks. The relative scarcity of detected carbonates has been termed the missing carbonate problem and suggests either that carbonate formation was inhibited by Mars water chemistry, or that carbonates are hidden beneath the surface or were destroyed through later processes. Small amounts of carbonates have been detected in Martian dust and in specific locations like the vicinity of Nili Fossae, where orbital spectroscopy revealed magnesium and iron carbonates. The Curiosity rover has detected calcium carbonate in drill samples from Gale Crater. However, the abundance is much lower than predicted by early atmospheric models, leading scientists to revise their understanding of early Mars's atmosphere and hydrological cycle. The detection of chloride salts in broad deposits scattered across Mars's southern highlands provides evidence for extensive evaporation of surface water. These chloride-rich deposits appear as relatively smooth, light-toned materials in low-lying areas within craters and valleys. Chlorides form when water evaporates and dissolved salts precipitate, similar to how salt deposits form in evaporating lakes on Earth. The widespread distribution of chloride deposits suggests Mars experienced numerous isolated bodies of water that evaporated to dryness. Zeolites, hydrated aluminosilicate minerals that form through alteration of volcanic glass by water, have been tentatively identified in some Martian soils. Zeolites can incorporate substantial water and would indicate water interacted with fresh volcanic deposits. On Earth, zeolites form in environments ranging from lakes to marine sediments to hydrothermal systems. Their presence on Mars would provide additional evidence for diverse, aqueous environments. The vertical distribution of hydrated minerals in the Martian crust indicates water activity extended to significant depths. Exposed crater walls and canyon cliffs show hydrated minerals appearing at depths up to several kilometers below the current surface. This suggests groundwater was not confined to shallow depths, but percolated through fractures and pore spaces deep into the crust, chemically altering rocks at depth. Deep groundwater systems could have persisted long after surface water disappeared, potentially providing refuges where microbial life could have survived if it ever existed. Seasonal processes continue to move water through the near-surface environment on present-day Mars. Observations have documented seasonal changes in slope streaks, brightness variations that appear on steep slopes in patterns that recur annually. While the exact mechanism remains debated, these features demonstrate that Mars's surface remains active, with processes involving some combination of dust movement, frost formation, and possibly small amounts of subsurface moisture. The regolith, or loose surface material covering Mars's bedrock, can absorb water vapor from the atmosphere through physical and chemical processes. Mineral surfaces can attract and hold water molecules through van der Waals forces. Additionally, certain minerals like perchlorates can chemically bind water. This adsorbed water may move through the regolith over diurnal and seasonal cycles as temperature and humidity change, creating a near-surface water cycle even in the absence of liquid water. Computer models simulating water movement through Martian regolith show that vapor diffusion can transport small amounts of water from depth toward the surface or vice versa, depending on temperature gradients. During daytime, warm surface temperatures drive water vapor downward. At night, cooling surfaces can cause water to migrate upward. Over seasonal cycles, water vapor could be exchanged between the atmosphere, near-surface regolith, and deeper layers. The implications of hydrated minerals for future Mars exploration are significant. Water bound in minerals can be extracted through heating, a process called pyrolysis. If regolith contains 1 to 5% water by mass, heating it to several hundred degrees Celsius would release this water as vapor that could be condensed and collected. This in-situ resource utilization could provide water for human missions without requiring access to polar ice or deep drilling. Understanding water on Mars continues to evolve as new missions arrive and instruments improve. The Mars Odyssey orbiter, which has been operating since 2001, continues to map subsurface hydrogen with its neutron spectrometer, gradually building a comprehensive global dataset spanning multiple Martian years. This long-term monitoring allows scientists to track any changes in ice distribution and better constrain seasonal variations. The Mars Reconnaissance Orbiter, which arrived in 2006, has revolutionized our view of Martian water through high-resolution imaging and spectroscopy. The HiRISE camera captures images at resolution down to 25 centimeters per pixel, allowing detailed examination of gullies, polar layered deposits, and potential modern water-related features. The CRISM spectrometer has mapped hydrated minerals across the planet. The SHARAD radar has probed subsurface ice deposits. Together, these instruments have provided the most comprehensive inventory yet of water on Mars. The MAVEN orbiter, studying Mars' upper atmosphere since 2014, has revealed how water escapes to space through measurements of hydrogen and deuterium in the exosphere. These measurements, combined with observations of water vapor in the lower atmosphere, have quantified present-day water loss rates and their variability. MAVEN has shown that escape is not steady, but fluctuates dramatically with season and dust storm activity. The European Space Agency's Mars Express orbiter, operating since 2003, carries the Marsis radar that has detected subsurface water ice and has searched for liquid water beneath the South Polar ice cap. In 2018, scientists reported Marsis had detected bright radar reflections from beneath the southern ice cap that they interpreted as evidence for liquid water, possibly a subglacial lake similar to those beneath Antarctic ice on Earth. However, subsequent analyses have questioned this interpretation, suggesting the bright reflections might come from layered ice with varying properties rather than liquid water. The Trace Gas Orbiter, part of the ExoMars program, has been studying Mars's atmosphere since 2018 with exceptional sensitivity. Its instruments can detect and map trace gases, including water vapor, with unprecedented precision. These measurements help constrain atmospheric processes and the vertical distribution of moisture, data crucial for understanding how water moves through the Martian atmosphere today. China's Tianwen-1 mission, which entered Mars orbit in 2021 and deployed the Zhurong rover to the surface, is providing new perspectives on Martian water. The rover landed in Utopia Planitia, a region with suspected subsurface ice, and carried instruments to study soil moisture and near-surface hydration. Ground-penetrating radar on the rover has probed subsurface structure to search for ice layers. The United Arab Emirates HOPE orbiter, also arrived in 2021, is focused on understanding Mars's atmospheric dynamics and seasonal cycles. Its instruments monitor water vapor, clouds, dust, and temperature across the planet, providing unprecedented temporal coverage that helps connect diurnal, seasonal, and interannual variability in Mars' water cycle. On the surface, NASA's Perseverance rover explores Jezero crater, caching samples that a future mission may return to Earth. Detailed laboratory analysis of Martian samples would provide orders of magnitude more information than can be obtained by remote instruments. Samples could be dated precisely using radiometric techniques, analyzed for trace elements and isotopes, examined for organic molecules with state-of-the-art instruments, and searched for potential biosignatures. Sample return represents a key priority for planetary science. Future missions will likely focus increasingly on identifying accessible water ice that could be utilized as a resource. Several proposed missions would land in ice-rich regions to characterize the ice properties, measure exact water content, and test extraction techniques. Understanding whether subsurface ice can be practically excavated, melted, and purified is critical for planning human missions that would need to use local water resources. The search for life on Mars is intimately connected to understanding water. Most life detection strategies focus on environments that had sustained liquid water in the past or might retain small amounts of moisture today. Perseverance's sample collection targets rocks that formed in the ancient lake environment where conditions may have been most favorable for life. Future missions might drill deeper to access groundwater environments or explore caves where ice might protect organic materials from radiation damage. Ice-penetrating rovers or submarines designed to explore beneath Mars's polar ice caps have been proposed. Such missions would face formidable engineering challenges, but could access environments isolated from the surface for millions of years. If liquid water exists beneath the ice, as potentially indicated by radar observations, such environments would be of extraordinary astrobiological interest despite the difficulty of reaching them. The possibility of liquid water in deep subsurface aquifers detected through seismic measurements presents both opportunity and challenge. This water represents a vast reservoir, but accessing it would require drilling capabilities far beyond current technology for Mars missions. However, if volcanic or impact heat created pathways for this deep water to reach nearer the surface, locations where such upwelling occurred in the past might be prime targets for investigation. Understanding water resources connects to long-term visions of human exploration and potential settlement. Water serves multiple purposes for human missions: drinking water for crews, oxygen production through electrolysis, hydrogen fuel for rockets and fuel cells, radiation shielding through hydrogen-rich materials, agriculture in greenhouses, and industrial processes. A human outpost on Mars would require several tons of water annually per person, making in situ water extraction nearly essential for sustained presence. Several strategies for water extraction have been proposed and tested in analog environments on Earth. For shallow subsurface ice, thermal extraction involves heating the ice-bearing soil and collecting water vapor that is driven off. For deeper ice, or in very cold regions, mechanical excavation might be more efficient, physically removing ice-rich material and processing it in heated chambers. Both approaches require significant power, likely from nuclear reactors or large solar arrays. Processing water on Mars would need to account for the salts and perchlorates known to exist in Martian soil. These contaminants would need to be removed through filtration, distillation, or chemical treatment before water could be used for drinking or agriculture. Fortunately, technologies for water purification are well developed, and adapting them for Martian conditions is considered feasible, though engineering challenges remain. The legal and ethical questions surrounding water use on Mars have begun to receive attention. International treaties like the Outer Space Treaty prohibit national appropriation of celestial bodies, but don't clearly address resource extraction. Whether water and other resources can be claimed and used by nations or private entities operating on Mars remains somewhat ambiguous. Additionally, if Mars harbors indigenous life, even microbial life, planetary protection protocols would need to prevent contamination of Martian ecosystems with Earth organisms, and extraction activities might be restricted. Climate models for early Mars have become increasingly sophisticated, attempting to explain how liquid water could have existed despite the faint young sun. Recent models have explored greenhouse effects from carbon dioxide combined with hydrogen, methane, or sulfur dioxide. Others have investigated whether impact events or volcanic eruptions could have triggered brief warm periods allowing temporary liquid water. Understanding ancient Mars climate is crucial for interpreting the geological evidence for water. Looking decades ahead, the picture of Martian water will continue to sharpen. Future missions will test current hypotheses, discover unexpected phenomena, and gradually piece together a complete history of water on the red planet. Each discovery brings new questions even as it answers previous ones, maintaining Mars as a vibrant frontier for scientific exploration. Water has shaped Mars profoundly. It carved the valley networks that snake through ancient highlands, filled lakes within craters, deposited sediments that became stone, altered minerals in the crust, and slowly escaped to space over eons. The story of Martian water is the story of planetary transformation, from a world where rivers might have flowed beneath cloudy skies to a frozen desert where moisture hides beneath dust and ice locks itself into polar caps. We have traced this water through its many forms and locations. In the polar ice caps that grow and shrink with the seasons, holding enough frozen water to cover the planet several tens of meters deep if melted. In the shallow subsurface at mid-latitudes, where ice begins just centimeters beneath your feet if you were standing there. In the ancient ocean that may have filled the northern lowlands, its shorelines now tilted and faded, but still whispered of by the land's shape. In the valley networks that record flowing water from billions of years past. In the thin moisture of the atmosphere, cycling between frost and vapor through each day and season. In the deuterium enrichment that reveals how much water has been lost. In the salts that might enable fleeting brines under the right conditions. In the mudstones of Gale Crater preserving an ancient lake's chemistry, in the minerals that bind water within their crystals, in the ongoing observations by orbiters and rovers that continue revealing Mars' hydrological secrets. The red planet remains an active world, Water moves through cycles between ice, vapor, and frost. Dust storms lift moisture to high altitudes where it escapes to space. Frost condenses and sublimates daily. Ice advances and retreats with the seasons. These processes continue today, connecting the present Mars to its water-rich past through an unbroken chain of transformation. For those seeking to understand planetary evolution, Mars serves as an invaluable natural laboratory. Its water history illustrates how planets change, how atmospheres evolve, how liquid water's presence or absence governs surface processes and, potentially, life itself. Every measurement of Martian water teaches lessons applicable to understanding Earth, understanding planets around other stars, understanding the conditions that make worlds habitable. The search for water on Mars continues with each new mission. Future explorers, whether robotic or human, will drill deeper, look more carefully, measure more precisely. They will find water in unexpected places, understand processes not yet imagined, and gradually complete the picture of how water behaves on a world so different yet so similar to Earth. Thank you for joining this quiet journey through the hydrology of Mars. If you found this exploration calming and informative, I invite you to like this video and subscribe to Nebula Nights. Subscribing helps me continue creating these detailed, restful journeys through cosmic topics, exploring the universe one peaceful fact at a time. There are many more mysteries waiting among the stars and planets, and together we can continue discovering them in this gentle, thorough way. Until the next journey, rest well.